Then let me introduce Professor Anita Behme. Anita is a professor, then is at Technische Universitat of Dresden, and she earns the share of applied stochastic there. She was invited professor at several universities, including Germany and the United States, and her interest is in probability theory and stochastic processes. Please, Anita, you can start.
Okay, thank you very much, and thanks for the invitation. I hope you can see my slides. And
we see them.
Okay, so I will talk about invariant measures of Levy type processes today, and that's a joint work with one of my PhD students, David Oechsler, who actually just submitted his thesis. But yeah, okay. So the motivation of my research comes from pictures like what you should see now here. So we have a stochastic process and we let time run. And what we are interested in are questions like what happens on the long run. So say, how does this process behave? Will it kind of converge to something that we can describe? So is there an invariant distribution that it will converge to? Is this invariant distribution unique? And under which conditions will it be obtained? And if there is a new unique invariant distribution, or if there are several, how can we describe them? How can we get properties of these distributions? So, and to tackle this question, I will split the talk into the three parts that you see here. So I will, of course, first tell you a bit background on invariant distributions. So what is it and how to treat it? And then we will see a rather recent result, namely a distributional equation that helps us to describe invariant distributions of so-called Levy type processes. And then in the third part of the talk, I will tell you about some special examples and related questions and where this all could be useful for. So let's start with the first part. So what is an invariant distribution and how to gain information about an invariant distribution of a certain stochastic process, assuming that such an invariant law exists. And the stochastic processes that I will consider are always one of these types. So you could have a Markov process, Levy type, Levy, whatever. We will see several examples later. Okay. So let's start with a rather general setting, or well, I want to treat Feller processes first because they are actually quite nice in this area of research. So let's consider we have a Feller process, so which is a time homogeneous Markov process. And this Markov process has some nice properties, analytical properties, namely the semigroup, which is actually defined down here, has some nice properties, the so-called Feller properties. So it maps the continuous functions vanishing at infinity on the continuous functions vanishing at infinity, and there's a certain continuity that we need. And well, such a process will be called a Feller process. And every Feller process is uniquely described by its generator, which is kind of the formal derivative of the semigroup. Namely, we can say that a probability distribution mu is invariant for a Feller process if and only if this integral here, so the integral over the generator applied on some function f, which is in the domain of the generator, this integral with respect to the law mu should be 0. Okay, so that's a standing known result. And this invariance property, well, actually I didn't yet define what it is. Well, for the Feller process, you could take this as a definition because it's an if and only if statement. But in general, you would say that for a Markov process, so for any Markov process with a certain semigroup, invariance is described like this. So what it says is like you have a kind of time shift invariance in your system, namely whether the semigroup acts on the function f, and this is integrated with respect to the invariant law, doesn't matter. So you have this equality here. Okay, so here's this TT, describes kind of the time shift under the process that we are considering. So that would be the general definition. And as I said, in the case of a Feller process, we have this equivalent statement here. So now I want to derive a first nice result about such invariant laws of a Feller process, because, well, if you actually look at this statement here, well, it's a classification of the invariant laws, but, well, what you need is this integral to be 0 for all functions in the domain of this generator. And typically, we even don't know what is the domain of the generator. So in some cases we have that, but often it's quite difficult to truly describe this domain. And then, well, how to check for something which has to hold for all functions in this domain if you even don't know what the domain is, that's quite hard. So so this is hard to apply. And to get to something much nicer, I want to shortly introduce what a rich Feller process is. So actually, richness here means that the domain is sufficiently large. So in particular, it means that the test functions are in the domain of the generator. And then in this case, we call the Feller process rich. And one has to be a bit careful here, because in some sources, such rich Feller processes are called Levy type processes, but that's not what I do. Okay, so here it's just a rich Feller process. So the domain is sufficiently large, and that means in this case, one can write the generator always in such a form. So you have here some integral. There's this function p of x and xi appearing, and that's the so-called symbol of the process. And then we have here the Fourier transform of f appearing. Well, so it's just a representation of this generator, which holds in many cases, say. And well, now if you take this together, well, that's an obvious thing. Okay, we have this representation. We want to describe invariant laws. So let's just plug this into this formula here. And then you end up with something like this. So far, I have nothing done. And well, again, this should hold for all functions f in the domain of the generator. So here is again this equation. So the integral, now it's a double integral, which has to be 0. And well, as I say, so this should be true for nice functions f. So in principle, the functions in the domain and actually the test functions and mu invariant. Well, and if you now take this formula and you just apply Fubini, well, let's just believe that it's possible, then we can take out this Fourier transform of the function f, and then you realize, well, if this should be 0 for all functions f in a sufficiently large set, well, then it can only hold if the inner integral is already 0. Right, so that's what we would end up. So we would need something like this. So now, well, this should hold now for Lebesgue almost all xi. And the good thing about this here is that actually the test functions, or the functions f from the domain of the generator, they have disappeared. So this is now a criterion for invariant distributions or invariant laws, which does not depend on anything like a function f. So you don't have to know anything about the domain in principle. So, and if you now put this all together, that's the theorem I published with Alexander Schnorr in 2015, or quite a while ago, then you end up with the following. So now we have for a rich Feller process in RD with a given symbol, we have two directions. So either we know that mu is an invariant probability distribution, and then you need some integrability condition, which comes from the fact that we wanted to apply Fubini. And then this invariant probability distribution will fulfill our equation as we just saw it. And vice versa, if we have a probability distribution, which again fulfills such a integrability condition and the equations that we just saw, then we can conclude that actually mu is invariant for this process X. So, and the good thing here is that no assumptions on the domain of the generator are needed anymore. So I want to apply this on a sort of, actually a toy example, namely on Levy processes. So for all those who do not know what a Levy process is, you can think of something like a Brownian motion, which is depicted here. You can think of Poisson processes like these ones here. Pure drift processes are Levy processes. In general, you have a process with stationary and independent increments. And so the process can jump, and it actually can have infinitely many jumps in any time interval. So that would give something like this here. It's a gamma process. But if you have never seen a Levy process before, just stick to the Brownian motion or Poisson process. Okay. And what I want to assume is that, well, I have a Levy process and I have an invariant probability distribution for this Levy process. Well, it is known that L is, so the Levy processes are rich Feller processes. And even more, since they are time and space homogeneous, the symbol that we just saw, so the symbol of the Feller process, is particularly simple because it does not depend on the first coordinate here. So it's just a function of xi, not of x. And well, we even know more. We actually know that it's given by the so-called Levy-Khinchin exponent of L, so which is the logarithm of the characteristic exponent of the Levy process L. Right, so we take here the characteristic function of the Levy process at time 1, and the logarithm of that is the so-called Levy-Khinchin exponent. And that uniquely describes the Levy process. And so we can use it here. So we have a very nice symbol in this case. We have this richness of the Feller process. And now let's say, well, okay, we take our equation here that I just showed you, and well, this should hold for all xi. And if you plug in this particularly simple symbol, what you realize is, well, it does not depend on x, so actually you can take it out of the integral because we only integrate with respect to x. And then you have here just this Levy-Khinchin exponent, and what remains, so if you take out this part, is just the characteristic function corresponding to the invariant probability distribution. And this would be the equation that you end up. Well, but we know that such a characteristic function is continuous, and actually in 0 it takes the value 1. And so for this to be true for all xi, we need that the Levy-Khinchin exponent of L is 0 near 0, at least near 0. And well, since we know what a Levy-Khinchin exponent is and it has some structure, this actually implies that this characteristic exponent, or the Levy-Khinchin exponent, will be 0 for all xi. And that says, well, the Levy process is 0. Well, and obviously the Levy process, which is constantly 0, is stationary. So it has a unique invariant law, but that's just a boring example because we have a Dirac measure in 0. So this was known, of course, but it's just a nice example of how to apply the theory of the symbol, because here we get a very simple proof that there are no invariant distributions of Levy processes, at least if you consider probability distributions and, well, taking out the trivial case. Okay, fine. So maybe let's look at a more sophisticated example. So here I take a generalized Ornstein-Uhlenbeck process. So that's defined as the solution to this SDE. So we have a stochastic differential equation, which is driven by two Levy processes, U and L. And I assume that they are actually independent. And then the solution is called generalized Ornstein-Uhlenbeck process. And well, why do I take such an example? Well, because in this case, actually, it's also quite nice because from this differential equation, we can directly write down the symbol of this process. So that's a result by René Schilling and Alexander Schnoor. And you see, well, actually, you see kind of how the structure of the SDE comes back. So you have here again these Levy-Khinchin exponents now of U and the one of L. And since L only appears additively, so you just get this Levy-Khinchin exponent of L as it is. And U here is multiplied, so we get here this X times Xi in the Levy-Khinchin exponent of U. Well, and moreover, we actually know that this is a rich Feller process. And now we can apply the theory I showed you before. So, and what we see is that, well, if we have an invariant probability distribution mu for this generalized Ornstein-Uhlenbeck process, and it fulfills a certain integrability condition, which in this case reads that we need a finite second moment, then we can plug in this symbol. So here that's a symbol. We can plug in the symbol in our equation. And, well, not fully solve it, but at least we get some expression like this one. So of course, this is much less easy to interpret than before with just the Levy process, but at least it's still some equation and you can work with that and try to get, show properties, at least maybe of this characteristic function of the invariant distribution. The obvious drawback of this is that we need to assume right from the beginning that we have this second moment. And well, if you just search for invariant probability distributions, it's obviously quite bad if you have to restrict beforehand to those probability distributions which have a certain moment condition, because at the end we don't know whether there would be more invariant distributions which do not have the second moment. So in going back to the theorem I showed you, so there's, except of this integrability conditions, that we need a number of other drawbacks, namely, well, I always restrict it to probability distributions, so I need finite measures for this theory to be applicable. And then I needed here this richness property, which kind of hides that I actually still need information about the domain of the generator. But maybe not as much as before, but still it's in here, right? So you still need to know that the test functions are in the domain of the generator. And otherwise, without this being rich, we couldn't make this conclusion that this implies actually invariance. So if you take out this last line, okay, maybe then you can still do something, but actually that's what we want to have, invariance, and not just this this integral equation. So so these are the drawbacks, and now let's talk about how to overcome some of these. So my next goal is to show you a distributional equation for invariant distributions, and now for the specific setting of Levy type processes, and I will say in a minute what these are. And so that will mean that we will actually get rid of a number of our conditions, namely we will completely get rid of the integrability condition. we will not need to tackle probability distributions anymore, but we can take infinite measures, so Radan measures actually. And instead of the Rich-Feller process, I will go to the Levy type process, which is also a larger class of processes in my notation. Okay. But the first thing I have to discuss here is then the question of now infinitesimal invariance versus invariance. And to go there, well, let's still start with the Rich-Feller process we just looked at in the last section. So again, let's take a Rich-Feller process with a certain generator. And then for this Rich-Feller process, one can show that the generator is always of this form. So we have some, yeah, you can interpret this as something like a drift term, some Gaussian component and some jump component, which are here described by some Borel measurable functions a and b, and this capital pi is a Levy kernel in RD, so that means that actually it's a Levy measure if you fix x, and otherwise it's just a Borel measurable function. And so why do I say, well, this is a drift, this is a Gaussian part, this is a jump part? Well, because this actually looks pretty much like the generator of a Levy process, just that now A, B, and this jump measure have become depending on X. So like you have a local behavior like a Levy process. So in every point X that you are, you behave like a Levy process, but depending on where you are, the behavior may change. So that's this X dependence which comes in here. And that's true for any Rich-Feller process, that at least for the test functions, you can write the generator in this form. And well, yeah, you write this, we say now that A, B, and this pi is the X-dependent Levy triplet or characteristic triplet of the process X, because that's how to describe the process uniquely. And we can actually split up the integral. That's what I will do in the following. So if you have this integral, I will actually split up this jump measure pi here into a measure of large jumps and a measure of small jumps, and then I can write it in these two terms here. So there's a measure nu, which corresponds to big jumps, and there's another measure mu, which corresponds to small jumps. And here are the integrability conditions for those two to hold. So actually splitting up is not uniquely, so we can find various choices for nu and mu. And in particular, the choice of nu and mu might influence this function a, but I won't go into details here. Just yeah, so anyway, it's always possible to split it up like this, and that's what we will do. And so what I will now consider is not this Rich-Feller process in the following, but what I want to consider is any time homogeneous Markov process who has a generator which looks like this. And that's what I will call a Levy type process. And that's actually a larger class than the just Rich-Feller processes. So Rich-Feller processes definitely are in there, but there are much more examples in the class of Levy type processes, which may be not Rich-Feller processes. And well, typical examples are like solutions of stochastic differential equations, like this generalized Ornstein-Uhlenbeck process that we have seen before, where actually we knew it was a Rich-Feller process. But here now the class can become much bigger, so we could take other functions phi, as long as they are, well, I wrote here nice, meaning, well, as long as they have some nice properties. Of course, you need some properties such that the SDE actually has a solution and so on. But that's what you can think of. So if you've never worked with Levy type processes, that would be the typical example to have in mind. A solution to a stochastic differential equation driven by a Levy process. Okay. And I showed you at the beginning this definition of invariance of a measure for a general Markov process. And now, since we are not rich Feller process anymore, actually not Feller process anymore, this is not equivalent to this equation here. So to distinguish these two, actually I will call a measure infinitesimal invariant whenever it fulfills this equation with respect to the generator. And recall, for a Feller process, this is the same as invariance, but in general, this is not true. So in general, what we have is that invariance will imply infinitesimal invariance, at least under some very mild conditions, but infinitesimal invariance does not necessarily imply invariance. And that's a bit of a problem because in principle, I'm interested in invariance, and if I can only show infinitesimal invariance, then well, there's still something missing. Anyway, so we will need this notion too. Okay, and then I can show you a first theorem on infinitesimal invariance. So what we have is now a Levy-type operator, which describes a certain process. And we assume that the test functions are in the domain for the moment. Actually, one can weaken this, but for the sake of simplicity in this talk, I will skip some details. And then we can show that a measure which is in a certain set of measures, I will say in a second what that is infinitesimally invariant for this generator, if and only if it solves this equation. So now this equation is meant in a distributional sense, so in the sense of Schwarz distributions. We have here the differential operator, we have here the Hessian matrix operator, and they have to be applied. And some other operators, V and W, I will say something about them in a second. So first of all, this set M of A, so the measure rho that I consider is in the set M of A, and this is exactly the set of radon measures which are such that all the terms that appear here are actually Schwarz distributions. That's sometimes hard to describe, and it depends on what you plug in for your coefficients, what these are, but in actually all cases of interest that we found, this would contain at least all finite measures and often actually also some infinite measures. But there you have to play around a bit with what you want to show or not. If you're good with finite measures, then actually this is not a real restriction here anyway. Well, to get a more, yeah, well, okay, so now this is an equation just like that. Well, you see that here's this A and the B and reappear from the generator, but I didn't explain what these are yet. So to get a bit more intuition what happens here and how to get this equation, I will shortly sketch the proof. So the whole idea is actually that we have this equation for infinitesimal invariance, and that's what we want to transform to the equation I just showed you. And to do that, one needs to rewrite the generator. Well, it's a similar idea to what I showed you in the beginning with a symbol. Here we won't use the symbol, but we just rewrite this generator. And in the one-dimensional case, actually one can find this in other papers as well. You can write this generator in such a form where what happens now is that so the first two terms are actually boring, but for the jump part here, you have to integrate now with respect to integrated tails of your jump measures. And then things are a bit more simple to write down. Well, yeah, integrated or double integrated tails actually. So in our theorem was actually posed in RD, so we want to do the same for a higher dimension. And to do that, one first has to decompose the whole jump measure, or actually the two jump measures, nu and mu, in a radial part and a spherical part, because otherwise you can't talk about tail integrals, of course. So, and now to be able to talk about tails, we take this radial part and the spherical part, decompose like this. And then you take the integrated tail for every point on the sphere, you integrate over the tail that goes out of this point, and that's what actually described here. So you have this an integrated tail, and what happens is that you integrate out over the radial part, while the spherical point is fixed. Well, and you do the same for the other measure, of course. And then you can also write down something which, like what I showed you before, now in higher dimensions, which is a bit more complicated than before, because now you need here to these directional derivatives appearing, right? So before that was just a derivative, now it's a directional derivative. But apart, it looks like before. And now, well, now we can take this representation of the generator and put it into our integral that we have seen before. And you can do this term by term, and you can start like here with the first term. If you have this one, well, you apply some nice rules for Schwarz distribution. So we assume, of course, that rho is such that this is describing a Schwarz distribution. And then you end up with something that you could write like this. So it's an operator that you apply on your function f. And the operator is given by minus gradient of a rho. And you do that for all the terms. So for the second, it's almost the same. And for the others, for the integrals, it's a bit more sophisticated. Namely, what you end up with are terms like this. So these are the operators. And now that's the explanation where this v and w come in that I actually showed you in the equation beforehand. So they are kind of operators that describe the jump behavior of the process. And yeah, in this particular form. And then, well, you plug everything together. So you say, okay, well, this equation is now 0 if and only if. Well, and this is the equation I showed you before. These operators here now, or these Schwarz distributions now, add up to 0. That's the whole idea. Okay. So functional analysis. And now let's come back to probability and retranslate this for stochastic processes and say, well, now we can say, okay, let's take some. Here I again formulated for the Rich-Feller process because I don't want to have too much technicalities here. So let's assume we have a Rich-Feller process. Then its generator is a Levy-type operator and it has this triplet. And we take any finite measure rho, and then we can say pretty much that if and only if rho solves our distributional equation, then it is invariant. Well, there's something we need actually here that the test functions contain a core of the generator. So that means if you know the generator and the test functions, you can extend it uniquely to the whole domain. So here's still some technicalities, but in principle, at least for this Rich-Feller process setting, our equation star is more or less, uniquely describing all invariant distributions, at least all finite distributions that are invariant. Okay. Now, of course, one would like to solve this equation star, but in general, that's not possible. I mean, you've seen the equation; it's not really easy to see how to solve it. But at least in dimension 1, it happens that actually you can write it as a sort of Volterra-Fredholm integral equation. So it has a name, and if things have a name, at least there's some theory on how to solve it. So it will have a certain form like this. I wrote down here what F1 and F2 are. So here you see the Gaussian part appearing. F2 actually still involves two constants. And these appear because we have to integrate our original equation twice. You recall there was this Hessian matrix in there, so we integrate everything twice, and then here we are the integration constants. And kappa 1 and kappa 2 are some suitable kernels you can write down explicitly in terms of the jump measures, but I didn't put them on the slide because they are just, yeah, it would be a bit too overloaded. But the good news is, okay, we have a sort of equation that we know how to tackle in some cases. And besides the fact that maybe one can solve it in some cases, it also helps a lot because you can easily get some information about the distribution. So for example, if we know that the term B of x in the generator is positive for all x, then every infinitesimally invariant measure is absolutely continuous with respect to the Lebesgue measure. So we always have a density. And that's actually easy to see because, well, we have here this Volterra-Freetorm integral equation. That's again the same as before. And now what you can do is, well, as long as B is not 0, you can divide by B and then you just see what the density is. Well, and you can do something similar whenever you know that there are no large jumps and the drift is non-zero. And then you can also show that all infinitesimally invariant measures and hence all invariant measures are actually absolutely continuous. So that's a rather general result on absolute continuity here. In dimension 1, but at least, well, in that case, you can do something. Okay, and now let's try to do this in a bit more specific settings. So the more information we have about our process, of course, the more we can say about the invariant distributions. And now I want to apply this whole theory in some concrete examples. So as I said, a lot of examples for these Levy-type processes stem from Levy-driven stochastic differential equations. And so now let's take a Levy process L in Rn, and it has a certain triplet A, B, pi. And actually I assume here, but that's also just because I want to say want things to fit on the slide. So I only assume that it has small jumps and no large jumps. So that will make my formulas a bit shorter. And then we have this characteristic exponent, as we have already discussed a few times. And here in this case, it will look like this because we have assumed that the other jump measure is 0. Okay. And now I can consider a stochastic differential equation of this type. And I want this function phi here to be, well, I wrote suitable. So what does mean suitable here? Well, I have some conditions on this, of course. First of all, I want it to be Lipschitz continuous in order to just have a unique solution to the stochastic differential equation. Then I want it to grow at most linearly. And then there's another condition here, which is kind of, yeah, the jump measure mu of the Levy process shouldn't have points of mass that kind of makes the process always jump back to 0 in a certain sense. So this assumption is exactly what you need for the solution of the STE to be a rich Feller process. So that was shown by Franziska Kühn in 2018. So, and if we make this assumption, we have a nice Feller process. And so I can apply all the theory above. And now I can write down, okay, and say, okay, any invariant measure rho of my solution of this STE will fulfill this equation. And so what happens now is that because I know the triplet of my Levy process and I know how phi works on this function x, you see what happens with the, you can write down like the triplet of the Feller process x and put this in the equation. And here this W is as before, so it describes the jumps of the resulting process, and the resulting process has a Levy kernel, which is, can be computed from the original Levy kernel of the process L. So that's rather explicit, at least for the theory here. And if you now really take a specific SDE, and let's just take the one you've seen before, so again, you take a generalized Ornstein-Uhlenbeck process with this specific SDE, then this whole theory would lead to something like the following equation. So now it looks ugly at first glance, but actually what happens is that you have here all the characteristics of the two Levy processes appearing. So the AL, the AU, the BL, BU, and then some other terms which come from the jumps of L and of U. And here it's again small jumps and big jumps. And one has to define what this is exactly, but in principle, this is a rather explicit equation. Still not easy to solve, but still it helps a lot to, well, you can use this, for example, to compute moments of this invariant distribution, or to show absolute continuity under certain conditions and so on. And this is also in particular interesting because this generalized Ornstein-Uhlenbeck process, the one I showed you, it's also known that the invariant distribution of this process is always a so-called exponential functional, namely it has a form of such an integral from 0 to infinity over, well, e to the minus another Levy process xi, and then with respect to L. And this process xi is, uniquely connected to the process u in this way. So it's a logarithm of the stochastic exponential of u. Anyway, so you can compute them one-to-one. And so given a u, you can compute xi and vice versa. And this invariant distribution is actually unique. And now with the theorem before, which also describes the invariant distribution of the generalized Ornstein-Uhlenbeck process, actually what we have is a description of the law of this exponential functional. And that's not only interesting because of this example of the generalized Ornstein-Uhlenbeck process, but also because these exponential functionals appear in various other settings, namely it can be used to describe certain survival probabilities of branching processes in random environment. They appear in the description of certain ruin probabilities for risk processes with investment and at various other places in probability theory. So this is an object of interest. And now with this whole theory of, well, knowing that this is an invariant distribution of a generalized Ornstein-Uhlenbeck process and describing this via this distributional equation, we can say something about this law and, well, for example, compute the law in some special cases or derive conditions for absolute continuity, compute formulas for the density and compute moments, as I said. So that's all where you can apply this whole theory. I should also mention that, well, of course, I now in many cases I restricted to these rich Feller processes, but in principle, the whole theory would also apply to non-Feller processes. So you could also take a stochastic differential equation like this. So here I have a Brownian motion in there as one driving process and a Poisson process. And I can choose here this phi such that it actually grows fast. And that will mean that we will not have a Feller property anymore. So this will violate the conditions that we had before, because you would have this term, with this phi here to violate the conditions. And so this is not a Feller process, but still we can use the whole theory. You can write down conditions for the invariant measure, because we can still write down what is the generator of this guy. You can write down the characteristic triplet, and you can insert this. And you can show, for example, that any invariant distribution of such a this SDE will have a density. You get some equation like this here for this invariant, for the density of the invariant distribution here, rho. And you can also show something like, well, for large x's, it will behave like 1/phi square, which is a typical behavior of the invariant distribution of a Brownian motion-driven SDE. So this is just to give you a glance of what is still possible, and to make clear that the whole theory also applies for such rather strange examples where typically things are difficult to work with. And then I want to tell you one last thing, namely a bit of an outlook of applying this whole theory for some Monte Carlo methods. And the idea is to use this equation star that we showed the other way around, namely to generate a Markov chain Monte Carlo method in continuous time. So we choose now a target measure rho, which could be, well, whatever measure, not necessarily smooth. So maybe it should have a density, but the density can be non-smooth. And now we can try to get to this target measure by the solution of a certain stochastic differential equation. I write it down like this. So actually we just have an additive drift here of an additive Levy noise, and then some function phi. And then we can say, okay, given a target measure and a suitable process L, which makes this target measure actually reachable, we can try to solve this equation star for phi. And then, well, here we have an example here of a computation. Well, this would be the Dresdner Frauenkirche. So that's our target density, which is actually not smooth because you have these jumps in here. And then we can create and simulate a process. Well, this is a process that you get, which is, in this case, it only has jumps of size 1 upwards, and then the drift. And the drift is made in such a way that in the end, you will get this histogram of your process. So this will be the invariant distribution that we can simulate from this SDE. And well, yeah, it matches the one we wanted quite well. And so that's another way to look at all this. So it also yields some nice results, which might be interesting for machine learning. So, but that's all I wanted to tell you. So thank you very much for your attention. And here are the main references.
Okay, thank you, Anita, for this nice talk. Are there any questions, please? Are there any questions, please? Could you hear me, first of all?
Yes, we can hear you.
Okay.
Thank you. Hey, everybody. Do you hear me?
Yes.
Yes,
Okay.
of course.
Thank you. A question related to the invariant measure mu. Is it the limit distribution of the Markov process X?
Well, yeah, typically yes, at least as long as you're ergodic. So that's something I did not discuss in this talk, but so what I only discussed is like invariance. So once you start with this distribution, you will keep it forever. What you talk about is like convergence to the unique invariant distribution, which would mean that you also need ergodicity of the process. So it will actually reach it wherever you start. That's not what I discussed, but yeah, once you have an ergodic process, this invariant distribution will also be the long-term distribution.
Okay. Thank you. Next.
Are there other questions, please? Okay.
I have a question. Muzaffar Fath. I can speak.
Yes.
Yes, of
Muzaffar.
course.
I ask about hypergroup. In 71, Shibli study Levy-Kenshin formula for Fillerian and for a second order operator for in more general form. And we with Dr. Wissam, we consider fractional power of using this Levy-Kenshin formula. So my question, yes, filler process, yes.
Mm-hmm.
We replace the shift x plus y by a more general shift. And the shift is interesting because everything is better. The Fourier is good, but only for Euclidean. But when we pass to other geometry for hyperbolic space.
So you mean replacing here the?
Yes, yes, this is another shift. And he get the same formula in 71. Is now around 50 years. I don't know.
Okay, yeah.
Yes, yes.
And
And
yeah, okay. So here in this case, we are only in RD with standard additive noise.
Yeah,
but yes,
I can't hear you very well. I have a problem in my so the shift is positive, but for Dinkel operator, when we change the in several variable in multi-dimension, is not positive. Is not positive operator. That means this shift corresponding to Dinkel don't conserve probability measure. And I ask if this is affect this your theory, the positivity of the shift.
Well, it might. We never looked at this because we were purely interested in this RD setting with additive also, yeah, additive processes. So I never looked at any other settings where you like have multiplicative processes or are living on a different geometry. But I guess it would definitely influence the theory. Yeah.
Yeah, thank you very much. Thank you very much.
Are there any other questions, please? Okay. Meanwhile, Anita, could you please go to the, let's say, third slide from the end?
Third from the end.
Yes, you had condition on phi and psi on that slide.
This one or
no,
before?
After. It will be after, at the end. Yes, go back, please. A little bit more.
No, that's the end.
Yes. Go back. Okay, perfect. No, the next, the one before. Sorry, you had the condition on phi and psi on the slide. Slowly. The one before.
Yeah, I know. There's a Feller case still. You mean here?
Yes. So you need phi to be bounded below by a power function.
Well, yeah, and here's this one, right? Yeah. Well, I needed to have the. I needed to have the solution of this STE to be a Feller process.
No, I mean, I think your inequality is reversed in that slide, on that slide. Because
this one? No. It's that's
no, this one, the other one. Sorry. Go ahead, please.
In the other case.
No.
I don't know.
Could you please go ahead?
So here, this is what I need for Feller. And then I can go to the non-Feller case. The non-Feller case, which is coming.
No, my question is with the other slide. The other slide, please, Anita. Go ahead, please. Just a little bit. I'm sorry because you don't have numbers on the slides. I cannot.
Here they are, down there.
Here. Then please stop. You just require phi to be bigger.
Yeah.
Do you mean bigger or really bigger or smaller?
No, here I really mean bigger. I mean, I want this not to be a Feller process. Because the Feller case is simpler. So here I'm out of the Feller regime. Meaning that I have a kind of strange STE.
For existence of the solution, right?
Yeah, one has to prove that first. Yeah, it's a lot of technical work. But yeah, you can show that this will not explode. The point is that the jump part here of n only comes in on a bounded support. Okay, so you have a certain regime where you may have the jumps, and outside it's just an STE by Brownian motion, and then you can actually allow for something like this to happen, and it will still work because you have a continuous process. But it's yeah, it needs some arguments, of course, that this actually has a solution, that the solution is unique, and so on. Yeah.
Okay, thank you. Are there any other questions, please?
Maybe for applications, real applications on of your mathematical results, or
yeah.
Or is it simply doing theory for theory? Or...
Well, no, it's not theory for theory, because well, I showed you here this, for example, this example, right? Well, these generalized Einstein-Uhlenbeck processes are used, for example, in finance as volatility model, or in risk modeling as a risk process with investment. And so if you know about the invariant distribution, or if you can describe anything about it, it will tell you something about like what the volatility does in your model, or what the like here's a ruin probability in your model does. And if you can, yeah, I mean, I think that's maybe not, I didn't apply this on data, but at least it's very important information for these models.
For these examples, I think that you work on R, not on RD. Do you think so?
In this case, yes, it's yes. In R, yeah. But you could make it multidimensional, actually. So such a thing also exists in D dimensions, and you can still say, okay, this might be now a D-dimensional risk process. and you would still get something like an exponential functional, which is a bit more difficult to write down. But yes, that's possible actually. But I only made it here in dimension 1 to keep it readable at least.
And what is the interpretation of the function phi in your because the theory is based on the function phi, okay, on your
the function phi in the SDE, you mean? So the one that we just looked at.
we had at the use in many slides the function phi, okay, and yeah. And what is the interpretation for example, if we consider the investment model or the ruin probability in risk processes, what is the interpretation of the function phi in your model?
Phi was just a function which, well, in this case, for example, you could write this as this right-hand side as phi of VT. And then you have a two-dimensional Levy process here, right? So that's hard to say what exactly phi is going to be. So if this would be like a volatility model, in volatility models, you would have like one of the processes typically to be deterministic. But like then you would get like the Kogarch model or the Barnoff-Nielsen-Shepard volatility. And yeah, but that's what this phi is doing here.
In a slide, you add in the differential equation, dxt is equal to a term, and you add phi something else. So I don't remember the number of the slide, but
this one
maybe.
So here we have, yeah, but that's, I mean, it's just just a special case, right? So again, I could use this as I could write this as one certain phi of xt minus, and then the two-dimensional process.
Okay.
But since I wanted to specify now that in this the first component you have this large growth here, and in the second component you have another condition, so that's why I wrote it in this form.
Decomposed. Okay. Thank you very much.
Okay, thank you. Other questions, please? Okay, then if there is no more questions, I would like to thank Anita for this very nice talk, and
It's been a pleasure.
see you soon in the next session. Thank you, Anita.
Thank you.
Thank you.
For listening.
Thank you very much.